So in this lesson, we're going to take a look at a specific technique that you can use to evaluate some somewhat more complicated integrals. This is the method that is called integration by substitution. It's also sometimes called change of variables. And basically, you guys are going to get to university, and they're going to review differentiation super quickly. They are going to move into integration, and they're going to teach you a seemingly endless list of techniques for evaluating integrals. This is the only sort of special technique that we need to know in this course. There's things like, integration by parts, like all these other things that you can do. You need to know this one technique for the AP exam, and then everything else will be kind of a big surprise to you when you get to university. So what is substitution or change of variables? It is basically the chain rule in reverse. Okay? So recall the chain rule. If we had something like y equals square root of x squared plus 1, and we wanted to do the derivative, we would take this and think of it as first x squared plus 1 to the 1/2, and then we would try to think of it as two functions that had been composed together. Think of it as, some outer function and some inner function, f at x and gx. For this one here, our outer function, f at x would be x to the 1/2, and our inner function would be the x squared plus 1 part. And I need an equal sign in between there. Okay? And then we would go ahead and we would do our derivative here. Sorry, not dy dx. Yeah, dy dx. Yeah, okay. Would be, again, we did 1/2 x squared plus 1. We kept the inner part exactly the same. Okay, then we had subtracted 1 from the exponent on our outer function, multiplied by the derivative of the inner function, and then we sort of canceled things a little bit. Okay? So substitution is basically the inverse of this chain rule for differentiation. When we were doing differentiation, if we were to write out the rule here, the derivative with respect to x of f at g at x was equal to f primed at g at x times g at x, g primed at x. What are we going to do in terms of integrals? Well, when we're doing integration, what we're going to say is that the integral of f primed evaluated at g at x times g primed at x. So if we're taking this thing over here and we're integrating it, okay, we're doing the opposite here. So if we integrate this, we are going to get something that is the composition of two functions plus a constant of integration. The way we make this integral easier to do is, as we're doing it, we are going to change variables by letting some other variable, usually u, stand in for this inner function g at x. Okay. So we take it, we define a different function that is not a composition of two functions. It'll be a function of a single variable by substituting in for that inner function. Okay. So what this makes our integral look like is we will be saying that, what am I doing here? Okay, integral of f primed x, oh, not at x, it's at g at x. So this integral that we're trying to evaluate, f primed at g at x times g primed at x. We're integrating over dx here. Same as up here. Okay. is going to end up being equal to some function evaluated at u. Okay? We're basically replacing this g at x by a different variable u. Now, if we look at what we have on the right side here, that f evaluated at u plus c is equal to the integral of the derivative of f at u, if instead of integrating over x, we're integrating over u. Okay? So basically, instead of just having capital F at u, we have the integral of the derivative of f at u. So what does all of this mean? Well, it means that this integral that we're trying to do, f at g at x times g primed at x over dx is going to be equal to the integral of this function f evaluated at u integrated over u, where we have replaced, we can make this substitution, u equals g at x. Okay? So this is basically sort of the formula. Okay? It's a little bit easier to understand in practice. So let's take a look at a few examples here. All right? Here's our first one. We want to do the integral of x squared minus 5 to the power of 8 times 2x dx. Okay? We're going to think kind of like we did when we were doing the chain rule. We look at our integral and we think, how can we think of this as an inner function and an outer function? I've set this one up kind of nicely so that we can think of this thing inside the brackets as our inner function. So our inner function, or our g at x, in this case is x squared minus 5. Okay, fair enough? Okay. This is the thing we're going to define as being our u. So this is our change of variables here. This thing, x squared minus 5, is going to be equal to our new variable u. So what happens if we take the derivative of u with respect to x? Okay. We get, well, if we take the derivative of x squared minus 5, we get 2x. Okay, straightforward. Now, the other thing we have to worry about is in here, we're integrating over dx. What is dx equal to if we do, because we're not going to be integrating over x anymore, we're going to be integrating over u. So we're going to get some integral that is an integral over a function of u times du. What is du equal here? Well, if we rearrange this expression, I'll write it underneath here, du is equal to 2x dx. Just rearranging it. So how can we change our integral here? We can change this integral that instead of x squared minus 5, we have a u. So x squared minus 5 to the 8 becomes u to the 8. This whole thing, 2x times dx, becomes du. So now we have the integral of u to the 8th times du. So we've replaced this tricky integral with something that's, well, more conceptually a little bit more simple. Okay? So how would you evaluate this integral here? U to the 8 times du. Well, how would you evaluate this guy? we're going to have something that is u to the 9 times 1 over 9 plus c. Now, we just make our substitution in reverse. We take this thing that we've defined as being u, and we substitute it back in here to get this in terms of x. So u is actually equal to x squared minus 5, so we get 1/9 x squared minus 5 all to the power of 9 plus c. Okay? So we take our complicated integral, make a substitution to turn it into something that's a little bit simpler, do our integration, and then do our substitution the other way. Okay. So let's take a look at another example here. Okay. We've got the integral of x squared divided by the square root of 1 minus x cubed, integrating over dx. How would you approach this one here? What would you do first? What would you think, Hayun? Okay, so let's write this as the integral of 1 minus x cubed, and we're going to change that square root to a negative 1/2. And then we'll keep our x squared dx just like this. Okay, so now we want to try to make a substitution here. Sort of identify this inner function and replace it with our variable u. So I think it's this thing inside the brackets that we're going to identify as being u, the 1 minus x cubed. So let's let u equal 1 minus x cubed. If we take the derivative of that, du dx is going to equal, well, what is du dx going to be here, Hayun? Negative 3x squared. So that tells us that du, if we rearrange that, okay, is going to be negative 3x squared dx. Okay. So let's look and see what we have back in our original integral. We can replace 1 minus x cubed right here with u. If we want to replace our differential here, this dx, we've got an x squared dx there. Here we've got an x squared dx, but we have this negative 3 out front. So the substitution that we want to make is going to be for this part here and this part here. So let's rearrange this expression to isolate that x squared dx. So x squared dx is equal to negative 1/3 du. Now we can go ahead and do our substitution in our integral. This is going to become the integral of, let's put our u in there, u to the negative 1/2 all times, to replace our x squared dx with negative 1/3 du. So instead of integrating over x, we're integrating over u. Okay. How can we approach this integral here? Well, the negative 1/3 we can just bring out front, and we can think of how we would do the integral of u to the negative 1/2. If we were doing differentiation, we would subtract 1, so we want to add 1 to our exponent here, so we're going to have u to the 1/2. And if we do the differentiation, that 1/2 is going to come down. We want something in front there that is going to cancel it out, so we can stick a 2 out front. Okay? 2 times u to the 1/2. And of course, it's an indefinite integral, so we add in our constant of integration. So, combining these two coefficients, we get negative 2/3 u to the 1/2 plus c. And then we undo the substitution that we've done. Negative 2/3, what is u? Well, u is 1 minus x cubed. So 1 minus x cubed all to the 1/2 plus c. And there's our integral. Okay. All right. Let's do one more example here. Integral of ln x over x dx. We want to make a substitution here. What might you try letting u be? It's got to be something that we see in this integral here. So what do you think, Daphne? See, if you let u equals x, then you're not really gaining anything by doing the substitution. So u has got to be some function of x. So what kind of a function of x do you see in that integral? Okay. It's worth a shot, right? Because it's the only thing that we see. Okay. So if u is equal to ln x, what is du dx? I do that on purpose to give you guys time to think. What is du dx here, Hayden? Okay. Which means that du, if we want to make our substitution, is going to be 1 over x dx. So how does this play out in our integral here? Well, our integral is ln x over x, or ln x times 1 over x dx. So this looks great. Now, if we substitute in u for ln x and du for 1 over x dx, our integral is the integral of u du. What's the integral of u over du? What do you think? We want to add 1 to the exponent, so we're going to get u squared. When we do the derivative, that's going to bring the 2 down, so we need something to cancel that out. So 1/2 u squared, indefinite integral, so we add in our constant of integration. And then we just make our substitution, undo our substitution. U is ln x, so our indefinite integral is 1/2 ln x squared plus c. Okay. So where do you actually end up applying this integration knowledge? Well, we've sort of learned a bunch of techniques we've learned like 2 techniques for evaluating integrals. And I started this whole section by saying that what we often wanted to do was find areas under the curve. Okay, so, hey, that's weird. Sorry about that. Now, what if instead of an indefinite integral, you have to do a definite integral here? Definite integral, you were given these 2 endpoints, a and b. The a and the b values that you're given our x values. If we want to do this substitution or this change of variables, we have to convert those into values of u to properly do our integration, if we're going to be integrating over u. But we know that u is just some function of x. So if we want to figure out what our u values are, we just have to evaluate this function at these two values of a and b. So our limits of integration a and b under, if we're integrating over x, if we're integrating over u, our limits of integration are going to be g at a and g at b. Okay? We use our function u equals g at x to convert from values of x to values of u. Okay? So let's take a look at how this works here. We got two examples that we can try. First one here, we want to do the definite integral from 1 to 9 of e to the root x over root x dx. What kind of substitution do you think you would make here? U has got to be some function of x. That function of x is going to appear somewhere in this integral. What do you think, Lee? You've got an idea? You don't want to? Yeah, root x. Or x to the 1/2. Okay. If we make that substitution, du dx would be 1/2 x to the negative 1/2. Okay. So du would be 1/2 x to the negative 1/2 times dx. Right. Now, we have an x to the negative 1/2 appearing in this integral. This integral is actually the integral from 1 to 9. That's not a 9. E to the root x times x to the negative 1/2 dx. If I take this 1 over root x, I can write it as x to the negative 1/2. Okay? So that looks pretty good down here in terms of our substitution. Okay? So what we can say here is that because we have an x to the 1/2 dx, we're going to make a substitution of this for this. We still have this factor of 1/2, so let's multiply both sides here by 2. So 2 du equals x to the negative 1/2 dx. Now, what about our limits of integration here? Okay. Our limits in our original integral are 1 and 9. So we've got a is x equals 1, b is x equals 9. We want to turn these into values of u if we're going to integrate over u instead of x. So if a is equal to 1, u is going to equal, well, u is equal to the root of x, so u is going to equal root 1. If b is equal to 9, okay, x equals 9, if we convert to integrating over u, our limit is going to be root 9, or 3. So if we do all of this substitution here, our integral is going to be the integral from, instead of from 1 to 9, from 1 to 3. Instead of e to the root x, we're going to have e to the u, because we've replaced root x by u. And instead of dx, or instead of x to the 1/2 dx, we're going to put in 2 du. And now we can do our integral. This constant just comes out front. Okay? So we want the integral from 1 to 3 of e to the u du. What is the integral of e to the u? Well, it's an exponential function. When you integrate an exponential function, it's like differentiating an exponential function. You just get the same function. So this is going to be 2 times e to the u, and then we evaluate it at the 2 endpoints, 3 and 1. Right, so we get 2 times e to the 3 minus e to the 1, which if we wanted an exact answer, we could just punch that into our calculator, and that would be that. Okay. Okay. All right.